When you cut out a zigzag ring of tetrahedra from a cube and insert hinges along their common edges, the resulting mechanical linkage has an unexpected freedom of motion. This motion was discovered by the Swiss engineer Paul Schatz in the 1920s and is known as the Schatz cube eversion. Coloring alternate hinges of this linkage in red and blue, we see that the three red edges meet together, as do the three blue ones. The red and blue meeting points determine an axis of symmetry of the linkage, shown in silver. The pieces of the cube are chosen to be as large as possible without blocking each other during the motion. At one moment they fit together exactly as they rotate through the middle of the space, and at the other extreme they form a large triangular hole. We can also double the original tetrahedral pieces so that they meet themselves in the center twice as often as the original tetrahedra do, and the triangular hole disappears. A similar variation replaces these tetrahedra, each with a pair of interlocked triangles. Finally, replacing each edge of the linkage with a piece of a doubly ruled surface produces an interesting effect. The outer faces of the original tetrahedra determine a closed polyhedron with 6 faces called a deltoid, which coincides with the cube at the beginning of the motion. There are 2 moments during the Schatz eversion at which strange things happen, and the deltoid degenerates into an infinite tetrahedron. At these moments, the 3 red edges are parallel, and the blue ones lie in a single plane, or vice versa. Paul Schatz used the motion of this linkage to generate a variety of surfaces, one of which we want to describe now. For this, we choose the so-called stick representation, in which we replace each tetrahedron with a simple bar. Schatz first observed that a diagonal of the linkage, joining opposite vertices, maintains its original length throughout the motion. He then fixed a bar of the linkage that has no common endpoint with the diagonal, and asked what surface is swept out by the moving diagonal segment. He thereby discovered a ruled surface he called the oloid. This shows how the oloid moves when we free the fixed link to move along with the original motion of the Schatz linkage. If instead we fix the opposite bar of the linkage, a twin oloid arises, swept out by the same diagonal. As the linkage moves, the 2 oloids roll around upon each other, touching along the moving diagonal segment. Paul Schatz applied the oloid to practical realms such as mixing machines and fluid propulsion. You can learn more about the Schatz linkage and the oloid by reading this book by Paul Schatz or by visiting the website of the Paul Schatz Foundation in Basel, Switzerland.